Is this on live or? Yes, I will click. Yeah, it's hard to drink water this way. It's a glass of you. Easier? No? Okay, so should we wait for some more time? So you could. Oh, so you could stay at home. Mistake, you know. So we'll wait for 5-10 minutes. Yeah. Sure.
Hello. I'm Anindita Adhikari. I work in the space of data analytics. So that's about me for a few years now, around 10 years. Thank you.
Yeah,
hello.
I guess, everybody could just say if they have any exposure to neural networks or not.
Hello all, I am Pratik. I'm a recent graduate MTech from IIT Kharagpur, and I have my background in deep learning for the healthcare application.
Hi, my name is Damien. I am a Senior Applied Scientist Manager in Microsoft, and I have written papers on deep learning and have quite a lot of exposure to deep learning in the web space. So I'm trying to learn more about applying deep learning in other areas.
Hi, I'm Abhinesh. I'm interning with a startup here called Incurs. I'm currently Incurs. So I'm currently working on a research project on emotion recognition, and it's on progress. Yeah.
Hi, I am Ankur. I work in Infi, and I have a warehousing experience. For me, ML and deep learning was a hobby till last year. Now I am working in some of the initiatives within my organization to leverage this ML and deep learning knowledge which I have gained over the past couple of years.
Hi, I am Senthil. I work in the areas of signal processing and wireless communication. So deep learning, I'm learning by myself. So that's it.
We'll get started also.
You're going to formally introduce me? Yeah. So maybe I can just introduce myself or go ahead. Yeah.
Hi all, I'm Diwakar. I work for Soliton for the past 3.5 years now. In the computer vision domain mostly. So in Soliton, the computer vision team, we mostly solve object detection, recognition, tracking problems. And then we have our own smart camera team as well, for which also we use to support and build applications for the smart camera. So yeah, that is, yeah, and then obviously we all use machine learning and deep learning things. And now we are getting started with NLP as well. So yeah, that is mostly my introduction. So with that, I'll just introduce Nishant also. So Nishant, I think other introduction he can give where he finished his bachelor's and all, but I'll just share my personal experience with him. So we had Nishant 1 year back also with us in the Bangalore Computer Vision meetup, where he spoke about the NLP introduction and then introduction to RNNs. And the session was really well received, and the people were asking more sessions on NLP. And we had 2 more sessions also on NLP side itself. And now we thought we should get him again to talk more about NLP, and he agreed to that, and he's here to speak about neural machine translation. So yeah, with that, I'll just hand it over to Nishant.
Thank you.
Thank you.
Thank you. I have my mic here. Thank you again, Salute on whole team to invite me to give a talk here. And feels very strange, you know, echoing from a small room. Yeah, that's okay. So, okay. Should I sit or stand? Okay. So the topic is neural machine translation. And yeah, so I short introduction. I used to work for IBM Research about till about 2.5, 3 years back, and since then I'm an independent consultant in the area of deep learning and applications of text, vision, and speech. I work across several domains, and I did about a PhD about 10 years back, and yeah, moved to India around 2011, and yeah, so let's get started. Okay. Yeah. So the talk is about neural machine translation. Machine translation means, you know, language have a sentence in one input language, English, convert into another language, Tamil, Hindi, German, Spanish, whatever. Yeah, and that's the problem domain. And I'll start off with sort of background of neural networks and RNNs, because one that is essential for understanding how the current machine translation techniques are implemented. Second, I also like to share a perspective that I have towards the whole thing, which is a new kind of programming, or if you have heard software 2.0, that term. So we're used to doing rule-based programming. When you write code in Python or Java, or the usual stuff, you write a web application, you write a shortest path algorithm, you're used to more writing a sequence of rules. Whereas machine learning, or what started off as machine learning, is more about writing programs with examples. You know, you're giving examples, you don't focus on the rules inside as much as examples on the outside. Okay, and so it's programming with examples and holes or parameters. Okay, so that's what I'd like to communicate. So it is useful. So machine learning, maybe it started off as a more pattern matching thing, but it gradually has taken up a whole. It has its own discipline of software engineering around it, and so that's why new kind of programming, and like we have scalars or real numbers in, you know, and on top of that you build lists and sets and dictionaries. That's software 1.0, the traditional one. Here you have vectors, lists of numbers, and then sets of vectors, matrices, sets of matrices, tensors. So, and that's the fundamental data structure. Okay, and the key operation here is the dot product. So having a background in linear algebra, or at least recalling the basics of linear algebra generally helps with understanding what's going on in these networks at a more semantic level. At the more syntactic level, you can just see the structure, but underneath, it's essentially these operations over vectors. And the key operation, there are number of operations. Okay, so dot product. I also have a board. I need a pen. Oh. So dot product. So I'm just starting from the basics, but x1, x2, right, like this. Okay, I shall make it x and y, x1 or xi, yi summation. Okay, everybody knows this. This is going to be the fundamental thing we are going. It's like plus operator or star operator that we use, or a list concatenation. It's as essential, and the whole, most of the machinery that you see around is just, you know, fundamentally built on this dot product. That's why. And what are weighted sums? So convert this x into a w weight. Okay, then apply wi, yi. Okay, simple. What is a weighted average? Weighted average is where the sum of Wi is, okay, or just divided by sum of Wi. Okay, so it has this interesting thing that, you know, you can 2y1 plus y2. If y has 2 dimensions, 2y1 plus y2 gives you an arbitrary big number, but you divide it by, you sort of interpolate between y2 points. So this normalization is the key operator. Okay, I'm just, we'll keep coming across this weighted average thing in what are called attention networks, and so when you see there, it's just, so I'm just quickly going through. Yeah, what's a function? A function is a mapping from, you know, given a sentence S, you map it to, this sentence is in English, this sentence is in German. So a function F maps a sentence from here. Our goal is to come up with these functions automatically. We don't want to write the rules for these functions. And neural network or a box with holes essentially helps you automatically generate this. You can, not just neural network, decision trees or just linear regression or logistic. They're all these boxes with holes, and they have their own algorithms of filling these holes from examples. Okay, and so the
because the language can like mapping cannot be properly, function definition cannot hold.
That's right. That's why you have these relations. So yeah, so a very simple example is child parent of relation. So you can see that P, or not, father of C. Okay, P is the father of C. It's a function on one father. Okay, but sibling have C1, C2, C3. C1 is sibling of three siblings. So it's a relation. So when you don't have this one-to-one mapping, there's essentially a relation of. So it's useful to visualize or model things in terms of relations. One sentence may have multiple translations. So it's best to sentence maps into a set of T1, T2. You can also write it as S1, T1, S2, T2. Okay. Am I just so okay? And why probabilities come in? So we are used when you're writing a web application, shortest path or whatever the standard algorithms or the standard. We are not used to thinking about probabilities. Okay, whereas this whole domain of machine learning and all is built around probabilities. Why is it so? Just a very fundamental question. Why are you forced to think about probabilities and struggle with it? Yeah, it's definitely. That's right. Right. Yeah. So basically, sorry. Yes. So lack of certainty, and these are more natural problems maybe as compared to more abstractly formulated discrete problems. And so, like for a sentence, there could be more than one translations. So not just, so you could just model by the relation, okay? But that's not sufficient. You want to give some weight or score to each of them, okay? And if you know that there are 10 translations, or if you have an image and it can either have a cat or a dog or a car, you know that there are 3 things. So you could model it as a relation, but better than that, you could just say that, you know, the cat has chance 3, dog has chance 4, car has chance 10, or score 10. And if you want to view it in a more normalized between 0, 1 range, you divide the thing by 4 plus 7, 17, and you get these probability scores. Okay, so relations, giving weights to each of the outputs, and then normalizing it. That's how you end up with probabilities. And the same with any domain where you have a number of outputs, you're not sure which one has more weight, and you want to compute in a systematic way how much weight to give to each. Okay, so that's yeah, very simple. If you want to, what is called language modeling. If you want to start a sentence with I, and you could write I am, or I will, or I go. So there are n number of possibilities here, but some of them are more probable, more weights. So you assign weights to it. This one particular. Okay, and when you start working with probabilities, and you maybe read papers or even basic notation, you start seeing these p y given x. Y is the output, input. So it's written in a functional style. So given x, you want to get y, but actually it means the relation that for a given x, there could be a number of y's, and each of them has some weight. Okay, and then you decompose them into. So think, should I try to explain what decomposition? So suppose you have to go from here to, the nearest mall, and if you plan that out, okay, so you have to first go down the stairs or elevator, then you have to wait for a cab and then the time taken to reach that mall. So it splits into 3 steps. Okay. Similarly, y given x. Now let me be just abstract and say that y has a number of components, y1, y2, yn, and x has x1, x2, xn. You can, in the simplest case, just say that y1 is dependent on x1 and nothing else. And so if you want to get y from x, you get y1 from x1 and y2 from x2, and so on, and sum up their probabilities. Okay, so this is how you decompose a bigger problem into a smaller. So decomposition is fundamental to our programming style. In any program you think of, you just try to decompose. With probabilities, you decompose things using a bunch of rules that satisfy probabilities. There are probably better ways to explain it, and there are different ways of decomposing it, which will you'll see these as I go through the. So just like you have to go from there to here to that. If you were standing close to the mall, you would just walk, not think about auto. So your decomposition doesn't have an auto. Mm-hmm.
For example, from English to Tamil, it's like English is like X1.
Right.
Tamil is Y1, Y2.
Right.
So Y1 depends on X1, but Y2 depends on X1, X2 plus also Y1.
Yes. So defining the decomposition can be tricky. There are many ways of defining it, and we will come to them there. So not if y1 and y2 are just words, you may not want words y1 to depend on x1. You want pairs of words, phrase to depend on x1, x2. So there's a variety of, and that's what people have developed across years to solve this problem systematically. Okay. So that was the high level background of underlying mathematics. Okay, so I am actually in 2 minds how slow to go, or is this too basic, too fundamental for everybody? It's okay. Okay, so then everybody knows about convolution. Okay, W, X, and a sequence of. Okay, sequence of each is at each place you do a dot product. That's why that dot product is important. And you do a sequence of dot products. So every time you collapse it into number, and sequence of numbers as output. Okay. So again, this is some of the motivation of why program with holes, but I'll just skip it. The parameters, I call the parameters the holes. Yeah. So and you have to fill in those holes by an algorithm. Yeah. So maybe if they are coming in, so I like to go back to the programming with holes and examples as I think it's fundamental to the different way in which we should think about it. Yeah, so if you have tried to predict stock markets or the curve the next day, you would know that this thing called moving average, simple moving and exponential moving average, and so on. Yeah, so if you write the formula, simple average is a sum of xt till n minus 1 divided by n. This simple thing. And exponential moving average is more weighted kind of thing. Okay, so these are useful formulas that help you predict. But suppose you want to come up with a new average or new kind of metric that is not easily definable in terms of it, but it helps to predict the next step. So what you'll do is that you'll take these x's and you take a bunch of parameters and put them together in a box and feed in lots of example of if my current x is this, what is the next x, and then expect the algorithm to learn these weights automatically. And the weights that the function that it might come up inside the box could be very new. You may not be able to understand it or interpret it, but it will definitely help you predict. So that's the so here you're writing rules which you think are useful. They are often you think they're enough to predict, but that's so that's what happened with images or people trying to classify images or understand sentences or speech to text. We're writing these rules for a long time, 30, 40 years, a huge amount of research, image gradients and various kinds of speech pre-processing, MFCC or whatever. So there are a bunch of rules that people wrote and they pushed the technology to be good enough, but not, well, to be good, but not good enough. And when the neural networks domain, method of programming came, you could, these rules will sort of learn automatically. Yeah. Okay. So, so the fundamental operator is dot product plus a bias, and all the operators. So I find it build mental. People must have taught you about convolutional networks and recurring in 100 different ways, and you must have read them. But I find it very simple to just view both of them as just for loops. Okay, for loops with holes, and so for I in range of n, where n is the number of say pixels or the length of the sentence, you write a function which essentially the idea is that in a convolutional network you can, if x is the input, then you can only access a window minus w plus w around the current position, and you're supposed to compute your output whatever it is by just looking at minus w and plus w. You're not, if you are at this position, you can only view this. Okay, this very rest you sort of pushed into a space, but thankfully or magically this is enough for a huge number of problems. For example, if you want to just figure out whether the image has a cat or a dog, this is just enough. You can just look locally at different positions, hierarchical way, and figure out what it is. RNNs, you have, it's like a while loop with accumulator. Okay, while I less than n, sum equals sum plus I. Okay. This is your RNN. You have this special accumulator variable. Just remember, I'm not sure what you call it, but let's call it accumulator. And at every iteration, that accumulator is updated with some function of I or some function of the previous value of accumulator and I. Okay. And so by having the sum, you are able to have a view into the infinite past, because some has in some way captured all the exercise that before, instead of a convolution network where you were only focused onto a window. Okay. Yeah. So having a loop view of both convolution and so essentially when you're trying to, suppose you are trying to analyze a sentence, okay, you want to find the category of a sentence. Okay, buy me a phone with 32 GB RAM. You want to predict that the category is mobile. Okay, so try to do it just this way with CNNs. Okay, what this means, you have to iterate over this. At every point, you can only look 2 steps back or 1 step back and 1 step forward. Okay. So when you look at buy, it doesn't tell you anything about it. Me doesn't. Phone definitely tells you about mobile, and 32 GB RAM maybe is similar. So you'll have an indicator 1 here, the rest of the position 0. Then you somehow compress that and get a 1. As that. Okay, so you roughly see how it works. Okay, you essentially trying to find indicators using these. And how do you come up with the fact that phone corresponds to mobile? That's where you use these boxes with features or I'm not sure how to. Essentially, you have a transformer which converts a phone to the mobile category, and that has to be learned automatically. Okay. So, and that's a good question, and that's why this view helps. So wherever you can sort of locally look into the thing and solve your problem, you're good. But where you need the whole history. So for example, images, CNNs, because you could locally detect edges and then combine edges to detect something more, and then detect eyes and face. So the local thing was. Whereas with sentences, you could. Yeah, I don't have a good example, but suppose you wanted to talk, I want to go to a bank of the blah, 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 and then the word river comes, river. Okay, so when you see the word river, then you know what the bank means, it's river bank. So there could be a huge distance gap between if it was the bank of blah, 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 Barclays or whatever. So that will change the meaning. So here you need this much of view into the sentence. Or if you are at the river, you need this much view back. And if you have a fixed window, you will not. Either your window has to be huge, which in some case will be not sufficient. So that case is right. It's a sentence, right? So sentence and CNN are two different things. So maybe you should repeat your question. Into a mobile category, yeah? Mobile category. Right.
Giving the exact sense of CNN rather than
yes, maybe because so maybe this simple example tells you that CNN is good enough to solve this problem. Maybe for classification problems, CNNs are good enough. Maybe this is going in the so the problems, many of the problems can be solved by CNNs and RNNs with equal performance and performance. But then the issues become how quick are you solving them, how quick are you learning. So CNNs have some amount of parallelism in them, whereas RNNs have a more sequential nature. You're running a for loop. So that's where the RNNs sort of start performing. If you can do a task well with CNNs, you generally stick to CNN. Yes. So I would say that the first classification efforts were of sentences were done with CNNs. There are several other issues here. I'm just glossing over. Having a word, it could be spelled wrong. Okay, and then you start looking at just character sequences, and then you have to compose these words from character sequences. All that could be done inside the framework of neural networks and CNNs, and that's where a lot of effort is spent if you want to analyze general, real world sentences or Twitter feeds, for example. Yeah, but CNNs are quite powerful. So I just wanted to make you have a unified model for thinking about CNNs and RNNs. Both are for loops. One has an accumulator which keeps track of the infinite past. Here you only have the small window. Yeah.
So my assumption till now was like CNN is something to do with image
Right.
CV, right? So are we saying we can apply the same CNN techniques with NLP, maybe when we have some very limited results to apply?
Yes, when to apply is a tricky question. It's not straightforward. So you can apply CNNs to natural language or speech, which has more than. You can apply RNNs to images also. Nobody stops you. There are a lot of people who have done that for different problems. So classification is just one of them. There are other segmentation problems, for example, with image, where you need to know the sequence, need the characteristics of the sequence more properly. That's where RNNs are more useful.
Okay. So the popular culture says RNNs are for NLP and CNNs are for
Yes, that's the sort of
research space. Things are like very much
Yeah, even in practice, people.
Line is blurred, probably I would say. I mean, in research space, you are saying we can apply both techniques in
That's right.
both areas.
Right.
But in the popular cultures, or maybe right now, what we are saying in the market, or maybe
Yeah, so
we are.
So the gap or the twist or the contrast or the fight between CNN and RNNs has been long, and it will continue from. There are several other reasons why you could both can be interchanged in them. And CNNs have a sense of parallelism. If we went detail into the construction of CNN, you'll see that there is a parallelism there which you can exploit. Whereas with RNNs, you have to have this accumulator. Once if you haven't computed the accumulator in the previous step, you can't go to the next step. Okay, so that makes it sequential and therefore less efficient. But it can this nature of function can actually solve a whole bunch of new problems that this narrow view cannot. Okay, good. So I have. So how do you fill in the holes? So these holes are these Fs here. Okay, I have just. And this function, how do you write these functions? These functions eventually come down to just this, some form of linear transformations plus squashing or a sigmoid-like thing, or things which squash a large number lines to 0, 1 region. The combination of these and nesting of these are what generally functions are. And the holes are the W's and B's. You don't know what linear transformation and what B to apply. And these are learned from examples. Okay, so how does it work? You provide a bunch of examples. I'm just covering machine learning 101 in a sort of convoluted or a different, more programming kind of approach. Okay, so you provide a bunch of examples. For example, for image classification, you provide image cat, image car, image tree. Okay, these are a bunch of examples. Provide a bunch of them. You set up your function inside the box with a bunch of holes, and then you start predicting. Okay, whatever the value of my W and B is, you predict something. Find the diff. If this is the image, I expected a car, I'm getting a dog. So diff, update my W's, update my holes, and keep continuing. If you have huge amount of data, you'll eventually learn these patterns if everything is good. Okay, so that's the principle of learning from examples and holes. Yeah, and the examples, the process of providing examples or different kind of examples is called supervision. there are 100 different ways of supervise these problems. And yeah, so for neural translation or translation problem, provide parallel pairs, what are called parallel pairs. Input text in English, output text in German. Okay, or whatever. You provide a huge number of them, and your machinery learns from those examples. Okay, there's one important factor, which is that to learn these functions have to be differentiable. Essentially, how do you say? The idea is that if you're very simplistic, if you can draw your function like a curve, then if you start at this point of prediction and you realize that you're wrong, you can just go down by the gradient of the curve and get to the right point. That's the simplistic 2D idea. But your data points are high dimensional. Images have like 256 cross 256 points. Sentences also can be embedded into so there's a huge space, high dimensional space, where you're supposed to start predicting from some place and gradually go down to the right place where the parameters are right so that they predict the right thing. Okay.
How many neurons are there in your model? So what do you mean by how many neurons are there?
Right. So there is this. So people, when they started talking about building neural networks, they and even now they work with analogy with brain neurons or what. Yeah, but when they were implemented with computers, they looked more like W's and B's. Okay, so when you draw a graph with a bunch of this layer and they're connected by those edges are essentially the W, the weights, which transform this layer to that layer. And you take a layer, the number of points it has, those are what are called the neurons. Yeah, so yeah, you can just think of the length of Y, the length of X. Each element is a bit. Yeah, so each element of that array is what is called a neuron. Okay, this is just to show you I mean, I guess most of you are familiar with how deep learning has taken over almost every, at least programs around images, speech, and text. We weren't able to write good programs maybe till 7, 8, 10 years back, as well as we can write them now. And this revolution has taken place due to very, very quick research based on these simple, learning from examples, these convolution recurrent primitives. And essentially, the approach has changed from when you were writing the rules to figure out where the mobile is or where the cloth is, to letting a network figure out the rules itself. That's the main shift in mental paradigm. And it's just an example of an image classification network where each node is these blue nodes are the convolution nodes. Okay, there are a huge number of. So you start with the image here and do these local operators, compute something, and then you do them again and compute more and more abstract features until you have figured out the right set of features that will distinguish whether the image has a car or a cat or a dog. And to work on huge number of categories that you see around the world, so many layers are required. That's what the several years of, at least 3 or 4 years of empirical experimentation taught people. That they started with a network this big in 2012, and then they figured out why it was not doing well, and they kept adding. There are sub patterns inside this network. Oh, the inception module is this. See this module being repeated everywhere, and this is the reason why that particular structure was designed to help you discover these features better. Okay, so that's just So this is the inception module, which has a bunch of convolutions of different kinds. So the weight or the convolution, you can have a bigger window, smaller window, rectangular, square, whatever. There's a number of choices here to design these networks. So it started off being in software. There's so many libraries that do that, but in hardware also there are implementations now. For the past few years there are. Okay, and one of the reasons they want to make it faster, so implement it directly in hardware. So FPGAs are one of the more flexible ways where. Okay, so we'll be focusing on RNNs, recurrent neural networks, because we want to the sentence we may have to look up a word which was long back before, and yeah. So mathematically, the same while loop that I wrote, sum equal plus equal to I, can be written in this way, where ht is the current accumulator, hidden state, x is the current input, I, and given ht and x, you compute the next hidden state. This is a very simplistic but almost full coverage representation of what RNNs do. And one way to implement F would be multiply ht by a vector, by a matrix. This is a transform it here, transform x, add a bias, apply a squashing function. Okay. We could spend a huge amount of time thinking why it is designed this way, but we have to cover a lot of ground today. So let's see, they're just transformed linear transformations of ht. So ht and x are in general vectors. So I'll come to, so images, you can think of numbers or matrices very easily. An image, take every point, the intensity at each point, and convert in number, and that's it. Sentences, words, you have to figure out a way to convert them into vectors, because the rest of the machinery works on vectors and tensors. Okay, so there's a way to convert words into vectors. So once you have a vector for a word and a vector for the accumulated sentence from the left, you can transform them and compute the next element or in the sentence. Yeah, maybe at this level, yes, but depending on the scale you are working on, you will have to concretize X into what is the element of interest. But nothing stops you. Any sequence of elements. It could be images also. You need not, or speech. Speech also, RNNs are a fundamental operator in analyzing speech to text. Sure. Yeah, you can ask your. That's right. So that's one of the problems. It's called language modeling, and so till now, so the talk is going to be about machine translation, which we haven't got there, and that there the problem is, given an input sentence in English, you have to convert it into German. Because that's the problem we are trying to. But the basics, the machinery involved is common to the problem that you said, predicting the next word or image classification. That's why I'm talking in a more general. Okay, so again, we could just spend a lot of time figuring out the different kinds of recurrence. So essentially, this F here is a box which takes in ht, the accumulator sum, and the current input x. And the way you design this box, there are 100 different ways, and people continue to write papers about how to design these boxes better. Okay. So two popular representations, one is called an LSTM, other is called a GRU, long short-term memory gated recurrent unit. Okay, these are two popular implementations of F, which are pretty ubiquitous. Everybody just, and there are libraries that provide you this implementation. You can just start off with a block of LSTM and GRU. The inside structure of an LSTM or GRU takes a bit of belaboring to understand, and yeah, and I am not sure whether I should go into it or not. Essentially, you have you want to get to the next state ht. You have the previous one ht minus 1, and to compute ht, you do a bunch of transformations inside it. Essentially, the idea is that you do a weighted average remember the weighted average that we talked to in the beginning, of ht minus 1, which is previous state, and a candidate new value. Okay, and what are the weights that there's a z, that those weights are also computed. So this is the f function here. Okay, it takes in you won't see the x right here, x is somewhere there. It takes in ht minus 1 and x is somewhere and computes the ht. And to compute this, you have to figure out where z came from and where h tilde t came. And there's a whole machinery to compute. Essentially, the idea is to compute z and h tilde, you combine again ht minus 1 and x in different ways and applies caution functions. Okay, so it's a vector, it's a hidden state. You can just remember the accumulator that we had. H generally comes from hidden state. So the LSTM or the RNN just starts with some accumulator state and the vector that keeps improving. Okay. Layers in the sense. Okay. So yes, I mean in general we'll have hidden layers. There's also a little bit of confusion about which direction we go with. We can go in two directions with hidden layers. No, so it's not the weights, it's the input. It's a sort of representation of inputs. So I wrote this function as a very simple while loop. Sum equals 0, while I is less than n, sum is equal to sum plus I. Okay, you could just generalize it to sum equal to some function of sum and I. So sum is h, the accumulator. So it's the interface between two blocks. That if you could view it that way, the box has the weights inside it. Okay, the weights are inside this f. How do you transform a sum and I to the new value? But what comes out at every stage is sum. What goes in is x or I. Okay, and just jumping to the x's or the i's are the words here, and h's are the sum are the vectors that sort of represent the compressed representation of the prefix of the sentence. In any sequence you're moving, you can just sort of compress it to the current h. Sorry? Yeah, so it's xt here. In the diagram, probably it's missing. Yeah, it's probably missing. It should feed in from somewhere because yeah, it feeds in here, it feeds in here, it feeds in here, it feeds in everywhere. It's just, yeah. So again, I have copied these diagrams from all over the web, and I have to thank, I couldn't just cite every slide with, but thanks to numerous people. So there's papers, but the learning in this field or the research has become very democratic. People have written lots of blogs and articles to explain and distill it even better than the original papers. So which actually helps us absorb and digest this in a more layman fashion. And that's something that is very peculiar that didn't used to happen as globally 10 years back. So there's also a learning revolution that happened. So anyways, yeah, so x is, so maybe, so x, yeah, these boxes are the weights here. X and ht minus get combined into what is called a reset gate. X and that reset gate and ht gets combined to the candidate h tilde t. And then you use this h tilde t here. And these weights z are also obtained by combining xt and these boxes are W, some weight matrices that are unique to every position. Okay, we could go into a huge amount of depth there, but let's keep going. Yeah.
It also looks like a kind of cause and effect where we take some updates and try to combine.
Yes, so basic autoregressive or basic recurrent equation, just this. This has huge number of a huge number of real life phenomena have been captured as this. Kalman filters is one of them. Okay, and yeah. So what happened, a lot of things which were, Kalman filter is again an example of handwritten rule, which was found to be very useful. A lot of those operations were now, converted into using RNNs. People started using RNNs where they didn't know what's the exact operation happening inside. Just in terms of these weights, it's something, but it generally started giving performance equal to those filters or even better.
Kalman having some system model, I think.
Right.
Then it uses it like based on the system model output and the measured output.
Right.
But here it's like there's no system model as well, it's learned.
Yes. So here the system model is given by the samples, input and output, and whatever the weights are inside, the input and output of the system is the input is a sentence, output sentence, input image, output class. So those are the only supervision you're giving it, and you're expecting these machines to learn the proper weights values here. That will, yeah. So essentially, what is happening? You are taking a real life object, an image or a sentence. You are mapping down to vectors or sets of vectors, transfers, and then you're doing a bunch of geometric transformation. These W's, multiplying it by W's is geometric. The bunch of scaling and rotating, and if you do it in a proper way, you'll get a representation of these vectors which are more amenable to what you want to represent output at the end. Okay, so instead of working on lists and sets and dictionaries and manipulating them as we do in usual programs, that was software 1.0, we work on vectors and transform them geometrically, in very complex ways to get to the desired output. Okay, that's the summary. So the problem that you were talking about, language modeling, essentially, if you have the sentence, the cat sat on the mat, okay, and you have generated this prefix, the cat, and you want to figure out whether the next word could be sat or not. So you write it down as the probability of sat, as opposed to you could also have a word on after this, cat on something, and there's probability of that. So that's the probability of generating the next word, is the problem of language modeling. And again, so how do I explain this? So the idea is, so the idea is that you've written cars here, you just think that these are words. So you take in the first word, maybe, okay, there are 3 layers or whatever. You just assume that the cat is the thing that is being fed here. And so the first level just takes the word the, it goes next level, then the cat word feeds in, then some other word feeds in, and at the end you predict the probability of the word sat. Okay, I don't think this is a good, for some reason I thought that this was a pretty good representation, but let me come back to this. I also had so I think it's important to first, so we'll be talking about sentences today, translation sentence, and so I just told you that you have to convert everything in this world of vectors and tensors. How do you convert a sentence into a tensor, a list of vectors? So it's not a trivial problem to do at all. And there are, again, 100 different ways of doing it. I'll tell you a very quick and very popular way of doing it, which is not this, what is written on the slide, so that you start getting some intuition. So suppose you are talking about news articles and you take, ndtv.com, you take all the words on the articles that you have. So you have word, India, government, democracy, whatever. You have a huge corpus of words. Okay, now you get a sentence that, GDP grows by X%. You have to convert this thing into a vector of numbers. Okay, sentence, it can automatically decompose into words. So if you can convert these words, you're done. You can just concatenate put them together. Okay, how do you convert GDP into a vector of numbers? So maybe right. Sorry. That's one way. That's called character level representation. So you can encode each of the alphabets into 0, 1, 2, 26 or whatever, 30, 50, and then just replace them by the numbers, and you'll get a yeah. Right. So that's what I'm coming to. Yeah. The problem with this character is that it depends on the length of the word, variable length, which can get you into problems later on. One more naive. So that is one naive way to do it. Another naive way to do it is just to collect the whole set of words that you'll be dealing with, assign numbers like a dictionary count to. Call this 1, call this 2, call this 3. Okay, so you'll have this word 10 and 20 and yeah. And again, these numbers don't represent, there's a better way to represent it. If you have like 200 words, you will have 200 length vector. And if GDP is there, set the 1, all of them are zeros. Grows, take the vector, 10th position to be 1, the rest of them are zeros. Okay, this is called one hot or term. Okay, there's a TF, IDF term where instead of just having number, you count the frequency of the words and then normalize it whatever and get the number there. The rest of them are zeros. There's a bunch of ways people have tried and used them for the usual set of problems, including translation in the past. So yeah. So more recently, so the problem with all of these is that these are very syntactic. You don't, by looking at these numbers, looking at the number for GDP and looking at the number for economics. Okay, this number will have 1 at 14th position. This number will have 1 at 102 position. You sort of, GDP and economics are sort of similar words, but you don't have any sense of similarity looking at the vectors. So these vectors don't actually capture the semantic meanings. Okay, so this is a huge drawback. And in spite of this drawback, people have used this representative for many tasks very successfully. Word embeddings are an approach to resolve that problem. Okay, essentially the idea is that I won't tell you again how it is computed, but I'll tell you the basic principle of it. So if the word GDP and economics, if you look at these documents, you'll find maybe these two words occurring nearby. Okay, so a word is defined by its context. Okay, so to represent a word as a vector, we'll choose these numbers, x1, x2, x3, x4, such that, so come up with these numbers somehow, okay, for economics, so that these two vectors are similar. Okay, and what does similarity mean? So similarity of vectors is very well defined in linear algebra. It's the dot product divided by whatever, but essentially it's defined by the dot product. So that's where we gain by mapping things to just pure vectors. That now you can use the basic operators on vectors to define similarity. Okay, so how? Yes, so I just simplified it to the, but the essential idea is you find the vectors so that they are similar. Similarity is defined by dot product. Okay, and so you have the whole corpus or a whole set of words, and you come up with these vectors in a particular way that if two words are occur nearby or are in occur nearby is the key principle, and similarity derives from that. So generally, if two words are similar in large pieces of text, they'll happen nearby. Most cases, again, that's generalizing, but yeah. So you come up with these vectors in this way, and we call them word embeddings. Okay, you could call them word vectors also. So the benefit was, actually it's on the next slide, yeah. But the benefit, I already told you that the vector for GDP and the vector for economics, if you take the dot product, the value would be high. They will be similar. It actually lets you use the machinery of vectors and linear algebra to model sentences. So sentences are strings of words. Yes, so compared to the default, the character-based simple 0-1 modeling, this definitely improves. Yeah, so yeah.
One example is basic arithmetic. You can do arithmetic with words. So it's like father minus boy, or you can do arithmetic, basic arithmetic.
Yeah. So
minus apple.
So this slide is there's a very systematic way of computing this vector, which I'm not covering. But if you have the vectors, you have a vector for man and woman and king and queen. Subtract. So subtract woman minus man, and you get a vector. Add that to king. You'll get queen. So it's that powerful. So these words which earlier the computer didn't understand, it's able to figure out because of these special representations.
You have to use a multi-dimensional space there, right? A semantic space, just you model them and then you put all these words.
Yeah, so you set up a constraint solving problem where you say that if these two words occur nearby, then the vector should have a high dot product. And you maximize that dot product for things that are nearby and minimize it for things that are far away. That's what, this technique called CB, or a continuous bag of words. There's a neural network-like structure which predicts from the context too. And there's elaborate theory. There are many different ways of computing this. So we are sort of, each slide is multiple years of research, and still there are people who are coming up with new ways of computing better word embeddings, which capture, so dog is an instance of animal. Okay, so your, or a better example could be, okay, so maybe the initial way you used to compute the word embeddings didn't capture the property that dog is an instance of an animal. So dog and animal vectors were still relatively far away, and not as much as you wanted. But with more improved techniques, you can have improved similarity in the sort of taxonometry and all that. So there, language and words are not simple to define even by human beings. We have been trained many years to do that. To train computers, there are a huge amount of effort required to let them understand. And word vector is the starting point. Yes. Yes.
It will be a cluster type of.
Yes. So all of them, there are many clusters, and you can go deep into the cluster and see. You'll find things that you may not want chair and table to be together. You may want chair and a seat to be together and table to be far away. But some cluster will have chair. So the process of generating those clusters is pretty complicated. But yeah, that's the space we work in. It is again the so it's not separate. It's fully embedded into the same machinery that I've been talking about. You train these vectors using examples. Examples are words which occur nearby and words which occur far off. So you want to improve for words happen nearby, and words that are far off, you want to reduce the similarity dot product cosine.
That happens before, for example, if you want
yes, so right. So that's also a good question. I'll just confuse you and say that it can happen before if you want, it can happen together with translation if you want. So you can set up since that is also a sort of neural network, a very high level intuition. This is also a neural network that computes this. You can compute it separately and take just the outputs and then work in a decoupled way, or you can just join the neural network with the final thing you want to do and do it in what is called an end-to-end manner. That's where the end-to-end thing. So these are very natural questions that come up when you try to decompose these big tasks into a smaller piece. And each of these units being so heavyweight already, and there are 15 different ways when you practice, when you try to implement them, the huge number of choices there, and you have to make good choices based on your judgment. Okay. Right. So I will hold that question. Common. So one way to use these things. So when people initially trained these vectors, they trained it for huge, like Wikipedia size, which is supposed to capture the whole meaning of the word or whatever. So, and then they collected these word embeddings and publicly opened. So word vectors, a thing called Glove from Stanford. After that, Facebook has fast text. And then there are even more recent embeddings which are. So these are all embeddings computed by similar algorithms, but the vector in one representation may not be exactly the same as. And you could pick any one of them and start off with your, for example, the classification task that we're done. You convert each of the. You have to first convert. You can't talk to a neural network if you don't convert a string word into a vector. So you have to pick one of them and start. Yes, so there are embeddings, or there are, if you understand, the embeddings which specifically capture those structures. For example,
one is hierarchy is already right. So for example, you have like parents,
which word vector I don't think it will, because
it will capture it to some extent.
So you look at like different embeddings, you capture it in extents. It's not like if you just train a word of compensation or something, you will actually see this. When you use vector math, you will actually see it.
So my question is like, it's based on similarity, so it will definitely form some sort of a cluster. But is there any word vector representation?
So so let me just, all representations will have clusters. There's no representation that, again, cluster is an artifact of these. You just group them together nearby. But so that's just the visual representation of it, or where they lie in hidden. Whether they capture similar meanings or not is a completely different question. And for that, you have to look at these vector operations of similarity, capture them. And some of them will capture the meaning better. Some of them will capture one kind of meaning, like taxonomy, better than other. But they will lose on some other front. And to get all compassing is still an open problem to get something that is. So again, there's a huge variety depending on how much capacity, how much expressiveness you want. So you start at maybe 50, go up to 2000 and 2000 bits or 2000 numbers, vectors for each. So the 2000 vector will capture a huge number of properties. You can think of sort of, it's not that way, but each bit captures some dimension of meaning. So whether it's a capital, whether it's a human being, you can think each of the bits. That's not right, but intuitively. So if you have 2000 dimensions, you're sort of capturing 2000 different aspects of this world in there. So again, maximum dimension required depends on the problem you want to solve. From 50 to 2000. 2000 is one of the higher ones. Generally, people stick with 300. But again, these numbers I don't think mean much. you're solving the problem doesn't really depend. It depends on several other things besides the dimension size. I'm right. Yeah. So there's a task, a concept of a task, which is whether you want to classify a sentence or translate a sentence or label a sentence in particular. These tasks can work with 50 or 300 or 1,000. And to improve on that task, the dimension may not matter. Something else will matter. The intermediate network will matter. Okay. So LSTM we talked about. By LSTM is another very favorite animal that roams around. And the idea is that you can do the for loop, you can go left to right. Okay, keep adding. You could also go right to left. Okay, and so you start with a vector, whatever. The sum is a vector, and you see a word, you update that vector, update. So that's what. So so this example is at the character level, not the word. So you have this word genetic. Look at the individual. Each thing gets converted into a vector. Okay, E gets connected. You see, these are unique vectors. Like you could get them, from a public source now. Now you run a while loop over them. That's what a LSTM does. So this is one LSTM that runs. You start with this, what is called a hidden state. There is a starting sum equal to 0 state. You take this vector in, you apply those W's, whatever I showed there. You get a new vector for after G. After E, you get another vector. At the end, you get another vector. Okay. And each point, so at this point, the vector sort of summarizes the meaning of G, E, and N. Okay. At this point, it summarizes the meaning of G and the set of characters. Okay. So this sort of, you're composing the meanings from the meanings of characters. By meaning, I mean the vector for it. You compose the meaning of the word. So this thing represents the word, starting from the meaning of the. And does that make sense? And similarly, you could go right to left. And you could start with the 0 vector here. And then what you do, you take these two vectors, which are, this captures the meaning left to right, this captures the meaning right to left. And sort of you have more meaning together than individually. So you put them together, concatenate them. Okay, concatenate is just another standard vector operation. And then that is what you call the word embedding. Okay, so from characters to words, you could go in this way also. So till now, we have been talking directly about this word embedding, and we can directly compute them. But we can also start from characters and get here through using this. So you see why the while loop is so important there. All of these are sequences. You can chunk it in anywhere and run a while loop over there, compute a representation. And then you can do that hierarchically. Okay, and there's something in between the character and word also called a subword. You could just take gen, have one representation for it, etic, have one, and then compose them. And these subwords are also important when you encounter very new words which were not in your dictionary. Okay, so yeah, so genetic came from here. Similarly, you have a human and a disorder. This is the sentence you had. Again, there is a LSTM that runs here, which composes them and you get a sentence embedding. And there's something called CRF, which you can use at the top, but this is good enough. So one way you can use it is that if you want to categorize this sentence into medicine, say human genetic order, you can compose the embedding. You can get the front and the end, put them together, get a vector, and say that this is the vector for my sentence. Okay, I have compressed the meaning of a sentence into this vector. And now I'll use this vector to classify. So I will transform that so that I'll get output medicine versus output mobile. So I'll have two outputs, medicine and mobile, and medicine will have high probability once you start from that way. Does that make sense? So that's the end-to-end thing. You start from these basic representation of subword or character units or words and transform them mostly through LSTMs and get the final sentence embedding. Again, this is one particular way of getting the embedding of a sentence. You would do it in several other ways. Yeah.
we are going towards right side. First line. Okay.
Yeah. So
G are predicting E, right? Kind of.
you could, so yeah, so what I was talking about is a different task where I want to take this sentence and predict medicine because the category is medicine, as opposed to mobiles, which were, yeah, and to do that task, that is different from predicting genetic given human.
Yeah.
That's a different task. Okay.
I was trying to understand why you.
Yeah. Okay. So okay, go, maybe you should ask the
So
question.
basically, when you go one direction, from after G you're predicting E, and then to V you're predicting L, and like that, right?
No, so you're not predicting; those are given.
Yeah, given. Right?
Given. Yeah.
So when you do the reverse order from C, you are kind of going.
Yeah.
I and all.
Yes, and the idea is that you can, if this was a sentence, it would more. So the bank and the river thing. If the river happens there, you can maybe get the meaning of the sentence earlier if you start from the right. So that's the intuition of why you go in both ways.
The notation of that 3 dots converted into 2 in second step. Yeah. First, the color code, step of G. 3
The
first layer.
first layer, the three bits, 3 dimensions.
Then how it's compressed to 2.
That's a choice. So the sum and the x's. These are the x's. This is sum. Okay, sum you could represent it by n length vector. This you could represent by m length vector. Here m is 3, n is 2. You could have made this 24 also. Okay, how do you come up with these numbers? Mostly empirically. People have been trying to solve problems for a long time using these, and they have figured out these right dimensions. I don't think there's much theoretical justification of why. Yeah, you'll see all sorts of numbers. Generally, the hidden, this is called a hidden layer, okay? Because it captures the summarized accumulator. And the 512 or 1024 is the typical representation for this layer. If it meant to the original author, I just copied the figure. Yeah, so my idea is just to, yeah. Okay, so we are now very close to starting on machine translation. And I wanted to, yeah, so one, now I'm maybe jumping and I don't know how to correct. One popular, yeah, so the philosophy or the understanding is that when you have an image, I'm switching to the image because there are many principles that apply. So you have this 256 by 256 image, those many pixels, 256 squared pixels. The core information in the image may not take those many pixels. Yeah, it's just a representation that we are familiar with. We can observe. If you have to really compress it, it would be very small, much smaller. And this sort of dimensionality compression is the principle behind, sort of this whole field. Okay, so one way it is exploited is that you can take the original image and transform it into what is called a compressed latent representation. Okay, and then try to recover the image from that representation. And this particular architecture or the way of doing thing is called an autoencoder. So it's not just image. You could take a sentence here, try to regenerate this. Okay, sentence converted into vectors, tensors, sort of gets compressed into a and then this has enough information to regenerate the same sentence. This principle is, I'm not talking about an application. What's a quick application here? PCA is similar. Captioning is a instance of translation task, which I'll come to very quickly. Label. Okay. So yeah, so this part is called the encoder, and I'm introducing the encoder and the decoder now. So so the previous slide, you could sort of think of this representation as the compressed representation for whole genetic. So if you just naively represent it, this genetic would be represented as a list of these vectors, or a vector of length 7 to 321 bits. But through this machinery, you can actually compress the information to a very small number of vectors. Okay, this, and I'm not saying, so there are many, so this compression would be in general lossful. You would lose some information. But again, if your problem requires, you would want to design the network in the way that you don't lose any information. Typically for the classification task, you don't need the whole information. Maybe genetic or disorder is good enough to tell you medicine, or some part of genetic in there. So you don't need all of it, you just need part. If you want to classify an face, that the face is there, you don't need the background or whatever. You just maybe need the eyes. 2 eyes are good enough to tell you. So there's many tasks just require compressed information to be successful, and this is where, so in general, so the encoder-decoder architecture, so the auto-encoder architecture sort of tries to compute a representation which is good enough to regenerate the whole thing. Okay, a slight modification of this architecture is the encoder-decoder, where you compress and find a representation so that you can map it to something else. So for example, with images, if you take a satellite photo or Google map, okay, that's what you feed in here. And here you want just the roads in the, so that's a subset of information there that has sort of a one-to-one corresponding with the actual thing. Okay, and so this architecture now helps you translate from one domain to another. And now that you understand how you can translate from image to text, which is the image captioning thing. You can translate from speech to text also. So all sort of translation can be done in this encoder-decoder architecture. It's a huge, very powerful architecture. Yes, and very differently. Again, the building blocks will remain these RNNs and GRUs, but the way you interact them, the way you number of layers you add, number of abstractions you compute, they will be very different. So okay. Yeah.
Common latent space cannot be getting based on the problem, what you are in goal, the way you create your latent space.
That's right. That's a very so people do try to compute a common. So there's a task called visual question answering, where you look at an image and ask a question you want to look at. So if you work in the common domain where images and text is embedded in the same domain, it becomes sort of easier. So people do try to do that. It's a more hard problem.
With the Google image, what is the satellite image? If I'm trying to find roads,
Right.
the kind of latent space might be, the way I have created latent space is different than when I try to look for rivers or
Yes. So I mean that statement is right. Just that it doesn't. There may be different ways of.
I encode my to the source.
Mm-hmm.
Will be different based on my problem statement, what I'm looking for.
Sure. That's the underlying thing. You encode them differently. So yeah, maybe that's a good way of saying that. Although we think more in terms of the architecture that generated latent space rather than thinking about the latent space. Right. Yeah. So and crafting that architecture requires a lot of cleverness or trickery. Yeah. Yes, we'll discuss the decoder in full detail very soon. So so this was one. This is a segmentation problem. You take an image and you try to figure out where the cars are, where the trees are. So this is a translation of image and this architecture. So a lot of these approaches are popular now. The segmentation task is particularly important for the medical domain, where you want to look at, for example, the eye or lungs or or the brain and the scans of them and figure out these areas of interest. And the same encoder-decoder architectures in a slide, which looks slightly different from the text ones, are used there also. Okay. And so coming to so this is one figure, the Google auto reply feature. So this again an encoder-decoder architecture. Is incoming mail, are you free tomorrow? That this is an LSTM. There are some internals which you can see here, and that gets compressed into this latent representation. And from that, you don't generate the same sentence. You generate a sort of translation of it, which is yes, what's up. Okay, and again, LSTM is responsible for generating.
Where is the supervised learning? You kind of previously kind of do some learning, and then you, based on that, you make the response.
So I haven't talked. So my starting point was these are these boxes with holes. You have to fill those holes. Only if you fill the holes right, you'll be able to generate the right sentence. Otherwise, you won't. Okay. Yeah. So I'm coming to that. So how do you fill the holes? I just want you to think about it for a moment. And there are holes all over. These W's are all over the place. And so the first principle is examples. Input and output, just the interface. You provide huge number of examples. Okay. And plus, that's not supervision comes with examples and the diffs or the loss function. So every time you compute something, you have to compare it with what you want, expect. And if there's an error, that error is extremely important. That is what helps you tune those holes. Okay, so program with examples and holes. And that's the principle behind the whole field across domains. Okay, so now we are coming to the machine translation business. Yeah. Sure. Mm-hmm.
How is that different? Is it another way of seeing? How is it different from a STM?
The components are the same. There's a LSTM. There's a while loop working here, and a while loop that generates the sentence. And but these while loops do different things. Here, the while loop is responsible for compressing this sentence into an embedding later. Yeah, you can, call it predicting the output, inference, whatever you want to call it. Yes. So is your question that the LSTM is used both in the sort of encoding and the inference part? So maybe we need to carefully look at here. The input is are you, and well, at a high level, this is the input and this is the output. Okay, that's a very high level. But then you decompose the task. Okay, so you decompose into the encoder part and the decoder part. What does the encoder do? It takes these word representation and computes this small thing, and the decoder takes this as the initializer state and does something different. It tries to predict the next word. Okay, so first word it takes just start symbol, just yes. Then it takes the word yes as input and tries to predict. Okay, so the way it works is different. So using the yes information of yes and this compressed representation from the past, it is able to generate words. Yes, the supervision is input and output. That's it. That's it. The rest of the internals is in the hand of the designer. Learning, learning. There are holes here. There are holes here. Yeah.
We have the same input and same output.
You want to generate it. And
there is narrowing down of the layers. Then it expands back in. So in encoder-decoder, do we still have the same network, just that the input and output are different?
The encoder and the decoder are different. Yeah.
expected output is not in the
Yes, that's right.
It's not like we are training half of the network separately and
No, we trend end to end because we are limited by the supervision we have. If you can give me better supervision, you can tell me what the thought vector for the sentence is, I'll be able to split this task.
maybe like we do autoencoder for the left side of which is the input and autoencoder for output and split these network into half and something like that.
Sure. So you can compute latent representations for the language itself in predicting next word business and then use it as a representation both here and here. Okay, so that is what is done in the newer architecture. Yeah. So the essential idea is that you have to capture the meaning of the sentence in these small vectors. And if you have captured it good enough, you can use it everywhere.
What I understood, like we have character encoding, then we have word encoding, then we have thought.
Sentence embedding. Yeah. Yeah. You're just.
Then we, then we have a reply or whatever is changed on the thought vector. Or word encoding, sentence encoding.
So I am not able to catch your stream of thought.
All are different problems. He has taken the sequence to explain us that was the character embedding, word embedding, and sentence embedding.
Yeah. Yeah. So all of that feeds in here. Yeah. Here, how do you convert from strings to vectors is a problem to be solved in many. Start from characters, word, blah, blah, blah. Once you get those vectors, then you have to encode the meaning of the sentence somehow. This is one particular way to do it. In this case, this is what is supposedly capturing the meaning of the sentence. And then using this meaning, I'm going to generate. Then you have to encode the meaning of the sentence. Who said? Okay. So what was the question?
So, like, for example, we have four states that shown like character.
Yes. So that is here.
Yeah, that's all happened. Like,
yeah.
What I understood is like similar to like word encoding, thought encoding, like sentence encoding is a next layer.
Yes, you can think. Yeah, and instead of representing it here, I'm representing here.
So after sentence encoding, we can use it even for translation or for example chat code.
Yeah, that's why that's the generality of it, and it's a representation of the sentence, and you can use it in many different ways. You can use it to predict the next sentence that would have followed in this email also. It's very powerful representation, and I'm going to surprise you again by saying that this is not a good enough representation for the sentence and we'll need to improve on it. But that's what the translation. So we'll be working with this encoder-decoder architecture for translation. Yeah, you could think of, instead of this reply, I generate the sentence in German. English sentence. Same overall architecture. The internals we'll see.
The way it's programmed, when you put audio free tomorrow, so only output will get us, right? You get
Right.
Probability, like MS WhatsApp, I guess day or something afternoon.
Yes, you can get a huge number of outputs. I'm thinking of the quickest way to. So here, what you say yes is actually a list of values. Okay, you have the whole vocabulary actually here. All the words that you could generate here and weights on it. Okay, and then you pick the one with highest weight, it turns out to be yes. So maybe the architecture part, how is being, sorry, what is the question? Yeah, so now you get it on LinkedIn also. You get a message and there's a short reply in the, okay, good, sounds good. And that's automatically generated. Yes, but you can have a list of auto replies. What if you get a new one, which first you have to build that list of replies that may not be suited to some mail that you get. So there could be new ones that don't fall in the list. So this system generates the new sentence on its own, a grammatically correct sentence on its own. Is that clear?
They have this all of our data. So basically, they are doing that mapping. We are writing the answers for them. So they are finding the best answers for. They are just ranking our answers.
Right. Yeah. So we supervise. So one way of explaining, we supervise Gmail's reply neural network by replying to these mails, and there are millions of people who have supervised it.
What I wonder is how should I give all the details how to reply, or like if you have a C3P or father, so he just knows everything, just a human being.
Right.
How
So.
It's just
So the
email you even put an output all programmed. Sometimes you have random output also. So obviously day to day you can also reply hard or cold randomly. So how independent is that output?
Yeah, so the principles behind it is statistics. It has seen lots of sentences. It has seen that this sentence is accompanied with this one in most cases, in majority cases, or they are top two candidates. And that is what it has learned through looking at so much data. And to learn it in a principled way, this is the architecture. This is the helpful machinery but that's the basic. So now your question has many aspects to it, how intelligent it is in a way. So you could, on one side is just statistics. The data that it has seen, it will only generate stuff that is similar to that data.
Everything is an assistant. You see, you tell the assistant that so random boss and tell them I'm going home. So tells the lady comes to tell some answer and tell them.
Right.
Doesn't can pick anything she wants. So something like that. Yeah. Also,
so the assistant. Yeah. So the assistant task is FAQ. Banks side have standard questions, standard replies. A human being to avoid a human effort in doing that, one could use this kind of machinery but FAQ is a very restricted domain, and the answers are sort of fixed for a given question. The problem is that once a user says the question, what does it map to in my database of questions? That's a tricky part. Again, these network examples will help you figure that out also. Okay. Essentially, human beings have done a lot of labor creating data, and now machineries can learn from it for specific tasks. And this is not magic. It takes huge amount of effort to do this correctly and nicely at the level of Google. But that's why they are Google.
I want to see like yes, no, thank you, something like that.
Other involved replies are also there. So it depends on the context of the data.
Are we on time or what is it?
Imagine that the same sentence was are you?
You can have a break. I'll
so now that is
just
and it hasn't that many examples of someone asking in a way. It will be confused. It will give some weird answer. Instead of are you free tomorrow? If you ask are you dying tomorrow in the same sentence, it has an encountered those sentences in that purpose. So it might give some weird answer to that.
Yeah. So if it so it generates data which is very similar, but again another effort behind these things is to make it slightly general. Okay, so we can have a quick break and come back and what are people